Okay.
Yeah, well, thanks very much, Manolis, for the invitation to do this. And only sorry that I couldn't be there with you guys. I think well, Crete is beautiful. Paris is okay, but it's a little gray today. So what I want to cover is the goal was the roadmap for SiPearl and for the ARM processors going forward. Um, I can't show our product roadmap because it's under NDA, and this audience is a bit broad for what we could cover. So what I'm going to do instead is talk a little bit, give you some background stuff a little bit, and then talk about where we see the market going, the trends, and then talk about what we see as important to do. And this will reflect our roadmap, but not specifically in terms of the products themselves. So with that, slide one. Okay, so I think most of you know SiPearl. If you don't, I'll have a little background right now. We're a fabless IC design house. We're based just outside of Paris, France. We have centers in Italy, in Bologna, and in Barcelona in Spain, and then 4 centers around France. And the reason for so many centers is to find talent. We're about 200 people from a lot of different companies. We've taped out our first generation Rhea. That was taped out in June. Um, our seed funding came through this consortium, I think most of you know, through the EPI, through the Euro HPC JU. And we've gone through our Series A. We just completed the Series A. It was a split Series A, and we just completed that. I'll talk about that in a second. Um, we are designing based on the ARM ISA, the ARM instruction set architecture. And we'll talk a little bit about why that is from a CPU perspective for server and how we think then that can help to move things forward in terms of other kinds of acceleration on other kinds of ISAs as well. So obviously sovereignty is an important element. This is part of the reason the EPI was created, the Euro HPC was created, so I'm not going to spend much time here, but this is somewhat the mission of the EPI and of companies deformed out of the EPI or not only companies, but also organizations linked to the EPI, is how do we grow more technology in Europe and how do we have a sovereign presence? A quick update because most of you know SiPearl, but we've had a little bit of a shuffling in terms of management. Some of you may know about this, some of you don't. So Ingshi, he's been with us since before SiPearl was a company. He has the role now of chief scientist. He's very much focused on manufacturing, packaging, specific technologies that we're working with. And advanced packaging is going to be certainly an important technology for us. This is where he really has an expertise, so he's applying that specifically to these elements. As a result of Vincent Casillas, I think many of you know him from the EPI as well, he's now our chief technical officer. So he's looking at how we develop relationships with partners, how we look at technology going forward in a broader sense. And then Gail Paul is our senior VP of engineering. So he's taken over the engineering group. Other than that, I think most of you know Anna, myself, our roles really haven't changed in terms of what we're doing. Now there's Gail there. I don't know if Gail, if you want to just say a quick hello.
Oh, just want to say hi to everybody. Thanks for hosting us. Really interested in all this consortium and what you guys are bringing to the party.
Okay. Just quickly then on the financing side. So we've closed our Series A. It was a split Series A. The final piece of that came in June of this year, right around the time of our tape out. So the total was 130 million. It was split over 75 million for the initial tranche, then an extension of 23 million at the beginning of 2025 and the final closing in June. We're now working on our Series B. So if you look at this in terms of how we were funded as a company, we got our seed funding out of the EPI, out of Euro HPC JU. This is really important to start the company at the beginning of 2020. And then the funding that we had Series A took a bit longer than we had initially hoped, and it was a split funding. But we're seeing a lot of momentum now around funding, and we're having a lot of discussions around our Series B round. There, we're looking to raise something on the order of 200 million. And that's already starting. Okay, Rhea 1, I think most of you know this, but just a quick recap on what we did there. It's 80 Neoverse V1 cores, so many gates. It's a single die with HBM on an interposer, so 2.5D packaging. And it's a fairly large package, 75 by 69, about almost 6,000, well, 5,500 pins. So the 4 HBM in package is about 64 gigabytes of memory in the HBM, and then we have 4 DDR channels as well. So it's in terms of the memory architecture itself, it's somewhat complex. To manage that, we have software tools that we help customers to place data in memory, either HBM or DDR. So it was quite an endeavor to put this together in the end, and there were a number of things we learned on Rhea 1. One of the elements that's been challenging was the HBM itself. HBM is really timed to work with accelerators, specifically with GPUs today. It's the most of the volume. And if we had our preference, we would work with generations previous in terms of CPU for the bandwidth, for the amount of memory, but the HBM itself tends to end of life fairly quickly. So in fact, the HBM2E that we use in Rhea 1 end of lifed before our tape out. So we actually had to buy the HBM2E that we need for production before we even taped out the processor. That's a challenge. And we'll look at that in terms of future generations and how we look at memory technologies and what are the best memory technologies to use for bandwidth, for latency, for capacity. In terms of Rhea 1, so it's equipped in Jupyter. Jupyter just had its inauguration event last Friday. We also have a reference design server. We call it the SEN platform. This is not a production server. We're not a production server house. We work with partners for that. Many of them are probably in this room, but that SEN reference platform is for us to do software porting. We're looking to have as flexible as possible a platform, and then it's used in a number of European projects, Sovereign Cloud and Sovereign COE. Many of you in this room are in some of those projects. The focus on the SEN platform is to be able to have either single CPU with accelerators in the chassis or dual CPU, or we could put 2 single CPU motherboards side by side and connect them over PCIe cables. We also have a couple of NIC cards in the back. We have a single power supply. Again, it's not a production server. The goal here is to make to allow people to be able to test ourselves, others, and do porting. And then we also have a SATA port sitting here that you can actually use for swap or storage, etc. So if we look at this, if we look at how we sit in Europe, really it's being part of a value chain in Europe. And the markets we're addressing here, we talked about servers, for instance. It's very important for us. We have what we consider direct customers and indirect customers, or end customers. And so our direct customers are people who either build servers, the OEMs, the ODMs, also the system integrators such as Megware, E4, 2CRSI. There are a number of them in Europe. So those are our direct customers. The indirect customers then are the HPC centers, the CSPs or MSPs, can be defense or enterprise customers as well in Europe. Anybody using a server, and we have to be in contact with them. We have to help them with porting, with support. But these are the customers of our customers. In fact, we spend a lot of time there. That's just part of the server market and how you go to market. One of the interesting elements that we looked at recently, and I thought this was worth sharing, if you look at the top computers in the world, obviously the top 2 computers in the world are right now in the US in terms of pure flops. But if you look at the green 500, you actually see that Europe is dominating here. And I think this has, I've seen some recent discussions, webinars, conferences where people are talking about, where is Europe in HPC, and, is this a race? Can we win? And the answer is the race is not about having the most flops necessarily. The race is about being able to develop workloads and develop competencies that you have in your territory. And I think this is a good reflection on where Europe is focusing, the fact that we're very strong in the green 500. We look at things like data privacy, we look at energy consumption. Our values are not anti other territories, but they're different. Now, I found this an interesting slide, so I thought I'd pull it and put it in. Okay, if we look now from a roadmap perspective, where are we going and why ARM? So today, if you're a CPU in the server market, there's really 3 choices. You can be x86, you can be PowerPC, or you can be ARM. And that's because of the software ecosystem. It's purely driven by the software ecosystem. So from a hardware perspective, you can design on many architectures. You could design server processors on many architectures. But if you look at the market going forward, this is from Gartner. There are many companies that do market analysis. Gartner is one of the top for server, so they're kind of a reference. But here you can see that there's growth in the server marketplace, but where you see most of the growth going forward is on ARM. You also see RISC-V starting to come up. That's a lot in the AI space and in the acceleration space, and that makes perfect sense. And then you see some other architectures that are still, PowerPC still has a small place in the server architecture. You even see some of the older Intel architectures that are still being sold. But that's really that blue piece of the market. If there's going to be any growth there, that's expected to be on RISC-V, and the other architectures are slowly dying, PowerPC included. It's slowly dropping out of the server marketplace. So if we look at the CAGR for ARM-based CPUs, it's about 20% year over year. And again, completely driven by the software ecosystem. So what we see from a CPU perspective for the future, well, I'll talk about this in a second, but I'm stealing my own thunder a little bit. The CPU has the flexibility to run many kinds of workloads. So we see accelerators more and more in this marketplace. Not everything can be accelerated or accelerated well. What's not accelerated should run on a CPU. In addition, the CPU should orchestrate the accelerator so that from a customer perspective, you see a simplified software stack and it looks like a CPU to you. That's the ideal. And as we see more and more kinds of accelerators coming into this marketplace, which is happening, then it's more and more imperative that the customer has a good out-of-the-box experience and a relatively simple way to access that acceleration through a CPU. If we look at ARM from the market players, so you have some rising players. Ampere Computing is in the market for about 5 years, Cypro, and then you have legacy players such as NVIDIA, Fujitsu. You now see ARM also offering some chiplets and even in some cases processors. And then the real driver for ARM has been the hyperscalers. The fact that AWS, Facebook or Meta, Microsoft, Google, Alibaba, I mean, not even showing China here, are working on ARM. This has really driven the ecosystem from the ISV perspective, the end application codes that are paid application codes, and getting that part of the ecosystem over on ARM. Now, if we look at RISC-V, we expect that adoption curve to be about the same. We expect that RISC-V from a CPU perspective should find first adoption in AI because the software stack will be, let's say, more limited there, more specific and a bit newer. But in terms of supporting the general server architecture, we think that's a little ways away before RISC-V on a CPU side is really broadly used. Between 5 and 10 years is our best guess, and we're talking to market analysts. And that's why it really makes sense for us to be on ARM today. But on the accelerator side, we see a lot of opportunity for whether it's RISC-V or something else. As long as the CPU is orchestrating that, that's a great place to try new architectures. Okay. In terms of our roadmap, as I said, I can't show you the roadmap. That's an NDA only presentation. But what I can do, Marc Duranton and Denis Dutoit and I put together a presentation for the ETP for HPC. It was a webinar that we did. These are public slides. It was presented in June. So I can talk about the trends here, and a lot of this matches where we see our roadmap going inside Perl and what we're targeting without specifically showing you the elements of the roadmap. Okay, if we look at trends in the industry, so more and more memory bandwidth, getting data to compute and having a good balanced compute architecture where you don't have stranded cores, you don't have stranded memory. This is getting more and more important. This has to do with a good energy efficient solution. We're seeing, again, the rise of ARM and RISC-V compute ISAs now in large compute and in server. Again, RISC-V, we see a lot, especially in acceleration today. There's a number of companies in the Bay Area. There's a number of companies here in Europe, and Europe sees this as a key vector going forward. We see more and more use of accelerators out of heterogeneous compute, and we'll talk about that a little bit. Interconnect technologies, memory technologies with higher and higher bandwidth and latency sensitive. And then with AI now, we see variable precision compute. And the big question is, what does this mean to HPC? And do we still keep 64-bit precision where it's needed? And where is it needed? And where could we use lower precision in conjunction with 64-bit compute? So this is something that's potentially driving the industry. Obviously, the slowing of Moore's law and the high cost of tape outs in advanced nodes, looking at chiplet, this gives you some opportunities to use mixed nodes, for instance, but it's very difficult for startups now to access 3 nanometer, 2 nanometer, 1.8 nanometer nodes. They're very expensive. The time to manufacture is very high. So finding ways that we can help companies to use different technologies or partner with other companies so that they can use joint technologies together is going to be more and more important, especially when we're competing with people in the market such as NVIDIA, AMD, Intel, who have deep pockets and who can afford to do both CPU and acceleration. And then advanced packaging, obviously with the slowing of Moore's law, you're seeing that packaging is becoming the place where there's more and more advancement. And we'll talk about that in a second as well. And then there are some side effects of this, one of which of course is reliability, silent data corruptions, and I'll talk a little bit about that as well in some of the slides. Okay, so obviously we're seeing a huge increase in compute over the last X number of years. 20 is a good number, but if you look from Blue Gene to El Capitan, it's a huge growth. We will continue to see growth. If you look back 20 years before that, you saw huge growth as well. But it's been an explosion, especially over the last 20 years in terms of HPC. And this is in flops, of course. With that, you see energy efficiency, but part of that is coming, especially in the last few years, from the increased use of acceleration. And we'll look at that. So if we look at, for instance, AI performance, so you see an absolute performance improvement in terms of energy over the last, let's say, 8 to 10 years, right? And you see that there's a point where we could start running certain kinds of models, GPT-3, GPT-4, as we had more compute available. So in a sense, the technology is making available now some of these models that people have thought about for a long time, but they didn't have the horsepower to run. In many respects, AI is brute force today, so we're just using pure compute in order to run these models. This will get smarter and smarter over time. So we'll figure out ways to be more efficient, but right now it's not efficiency, it's a race to performance. If we look at that, one of the ways we've made these gains in AI is, sorry, I didn't build this out, is by data coding. Again, moving from FP64 to FP4 or even lower. So that's a big gain, but that's a one shot. Once you move to FP4, you're not going to see gains going down to FP.0000001 or something like this, right? So that was a way that we gained a lot of efficiency, but the further gains in efficiency are going to have to be through efficient use of codes or technological innovations, not just data coding. So how do we look at this? How do we develop on this trend? The other key thing here is looking at Moore's law and how Moore's law is slowing, but we're finding ways to advance beyond Moore's law in terms of just process nodes themselves. Another way to look at this is in terms of computing performance. And if you see the high end of computing performance here is very much on acceleration, TPUs and GPUs. But we see that memory capacity and bandwidth interconnect are lagging behind. So again, how do we build compute that doesn't leave elements stranded across a wide number of workloads? The other trend that we see here is that we have larger and larger AI models. Now, that's going to hit a point as well, but right now we're just pushing the hardware technology as fast as we can to build bigger and bigger models. And it's a land race to build larger and larger models. In terms of these modules, these models themselves, if we look at industry analysts, they expect that 2027, 2028, we're going to hit a wall in terms of data and training, in terms of the size of the models that we can actually run efficiently, and in terms of energy. And so they expect then that there'll be this land race for more and more larger and larger models will tail off, and people will start looking at, now, how am I making money on my inference? Now, people say 2024 was the year of inference. That's true in a respect, that the large data centers opened to customers and customers ran workloads, but these data centers weren't making money. They were just, again, trying to grab market share, and that's the race right now. So we expect 2027, 28 is where now going from trying to grab market share goes to figuring out how we actually make money in this space and where do we get a return on investment. And that's where we expect other kinds of acceleration beyond just GPUs to be used for the inference side. Today, most of the inference, you do the training on a GPU, you use that same GPU then for inference when you have customers coming to you. It's not efficient, but it's an efficient use of the resources that you have in a sense. So again, finding a way to balance the memory capacity, interconnect bandwidth with the compute elements themselves is going to be important going forward. And this gap right now is growing, again, as there's a land race. So if we look at this from year-over-year evolution in compute elements, back in 2000, you went from single core to multi-core. And multi-core architectures required a change in software, so there was a resistance that only happened once we ran into the frequency wall, where we couldn't really run beyond 4 or 5 gig efficiently. And then in the 2010s, we started to run into a power wall, so you started to see more acceleration being used in heterogeneous architectures. And they took a long time to adopt en masse, but today you see large numbers of GPUs, for instance, being used in HPC centers. And again, there was a lot of software development work that had to be done there to make sure that you could run those accelerators alongside the CPUs. Where we see things going forward from now is we're starting to run into cost issues, the reticule size and cost issues in terms of the manufacturing itself. And so here, moving to the chiplet architectures makes sense. The packaging now, I mean, AMD really opened the door for this, but the packaging now is advancing more and more. And in the chiplet architectures, you now split your architecture. You can have multiple companies actually working together so they can split this cost. You can have different node technologies. So if you need to be in 3 nanometer, you can be 3 nanometer. If 20 nanometer is good enough, you could be in 20 nanometer. The only requirement would be that you can actually connect the die together, so the interfaces have to actually fit. And if you need coherence, then you need to address that in terms of the NOCs themselves. But here now in the chiplet architectures, this is where we see the market going. People talk about a chiplet marketplace where you could just buy chiplets and then plug them in. That's probably not going to happen, and certainly not before the 2030s, and probably not before 2035. There's a lot of work that has to be done on the ecosystem, both on the manufacturing side, on the software side, on the interface side, packaging. All of this has to be managed. But today you see multiple companies working together, and that will happen more and more between, let's say, now and the end of this decade, where you have multiple companies working together to build chiplet solutions, but it has to be done in cooperation. It's not like you're buying something off the shelf. So that's where we see the market going right now. This gives you flexibility and performance scalability, but the partitioning, the architecture partitioning and the software partitioning is particularly important, and you have to get it right. So if we look at this new paradigm moving toward what we call system of chiplet. So if you look at the classic Moore architecture, you're starting to drop off, but this idea of a sysmore, you can actually drive gains more and more. And this is where the advanced packaging becomes important. There are a number of challenges there, managing heat, stresses within the package themselves, the cost of the package, how do you do testing, how do you do in-package testing. So there's a number of things we have to figure out as an ecosystem before this becomes off the shelf. But it's certainly from a performance perspective, you see that this is a way that we can start to get gains back that we're losing based on just processing nodes themselves. And in terms of the application trends, so we see more and more processing power required, the data sets changing with AI, security becoming more and more important, trying to reuse what legacy we can, but then more and more modularity and more scalability. So how do we scale down from low to very strong processing nodes? The value, the elements that you get from a system on chip or system of chiplet versus a monolithic solution. So again, these chiplets can be in different processing nodes, and they could even be from different companies. So if we look at, for instance, Cypro and how we look at our roadmap going forward, who do we compete with? We compete with AMD, Intel, NVIDIA, potentially ARM. There are other people in the world like Fujitsu. We may not compete directly with them, but we're doing similar things that they're doing. We don't have deep enough pockets to spend on CPU and accelerator and all the, we can't be in every fab. We don't have the buying power within TSMC that, say, NVIDIA has, for instance, or Apple has, for instance. So working in partnership with other companies, having other people develop accelerators that we work with and orchestrate so that they have a solution that, from a software perspective and an end user perspective, an out of the box perspective, helps them to be easy to use. And from our perspective, it gives us a variation on compute. This is what makes sense for Cypro, and we think this is what makes sense for Europe. This was expressed in the idea of a common platform at the beginning of EPI. Now, the common platform itself is sort of easy to say and hard to do. How do you actually drop things into an existing package? Who designs for that? What's the time frame of the lifetime of that package? But one thing to note, if you're in 3 nanometer, even 5 nanometer, your tape out costs are on the order of 20 million. Building a new package is on the order of 5 million. So as long as you have the interfaces working together between CPU and accelerator, as long as you have the software solution that you've worked together to create so that from an end customer perspective, they can access the acceleration elements in a reasonable and let's say, orchestrated way, then you can develop together something much cheaper and variations on products much cheaper, because now you're talking about package options as opposed to going through fab again. So we see this as very exciting for the future. Now, again, chiplet marketplace, where you're taking things off the shelf, probably not before 2030. But we have customers today coming to us looking for known good CPU dies, and we see opportunities to develop solutions in conjunction with other partners in Europe doing acceleration, where we can create compute solutions that take advantage of the ARM architecture and the fact that the software ecosystem works on the CPU, but then can get advantage of the acceleration with other architectures like RISC-V or even custom architectures. So that's what we think makes sense for Cypro and for the future of Europe. If we look at that from a holistic point of view, then obviously you have to look at this, up from technology, whether it's manufacturing technology, packaging technology. You have to be able to segment the architecture in a clever way and make sure that you take advantage of the different elements so you get the strengths and not the weaknesses of each of the elements. And you have to look at, obviously things like bandwidth between elements, latency between elements. Where do you see advantage being in package versus out of package? There will be some acceleration that you don't need to put in package, for instance. So how do you emulate this up front and understand your performance gains that you will get? In terms of data coding itself for the different kinds of workloads you run, the key is really the software stack. And you see this with NVIDIA, with CUDA. But how do you allow the CPU to orchestrate the acceleration so you get advantage of the features you want, but from the end customer point of view, they see what looks like a CPU, and a CPU that runs in their existing ecosystem? That's key. Obviously, programmer languages and the applications themselves, porting and making sure that they run well, and such as Filippo was talking about in his previous discussion. So if we look at where we think the market's going and where our roadmap will reflect, it's really around chiplets. And in Europe, it's really around companies working together to be able to create compute elements that are accelerated, but run as easy as possible, let's say, with as little complexity as needed for the end customers to be able to access this. I think I'm pretty close to, I think I overran my time. I'm not sure, but that's what I wanted to present today. Any questions?
Thank you very much, Craig. We will ask now if there are comments, questions from the audience. Well, Craig, from my side, a comment on your discussion of system of chiplets. Probably we're playing a bit on words here, but what how would you classify the Rhea 1? Is it a chiplet system? Is it a
So if I look at
chiplet-based
Rhea 1, I would say it's monolithic. You do have HBM in package, so you need the interposer, and it's fairly complex from that perspective.
Right.
But
Right.
the main chiplet itself is a monolithic architecture.
It's a monolithic, right?
With Rhea 2, we'll be going to chiplets, and then generations beyond will be becoming more complex in terms of chiplet solutions.
Right. And in terms of the interposer technology, do you think that what is currently available, do you think is sufficient? Do you see a need for an upgrade there? Is there a roadmap for such upgrades? Kind of open-ended question, and obviously not committing on your side.
Sure. So if we look at the technology on the interposer side, so right now the interposer is fairly expensive. If we can get to organic interposers, that saves some cost, but there are some limitations for organic in terms of the size you can have and the scale of the processor itself. Obviously, if you can stack chips one on the other and eliminate interposers, then you do save some cost. This adds other challenges in the package itself. So this idea of 3D packaging instead of 2.5D. 2.5D is when you're both sitting on an interposer, and 3D is when you're actually stacking chips on chips, or a combination of 2.5D and 3D. So these are things we're absolutely looking at. As packaging technology evolves, getting cost out of the system and getting, heat out of the package are two key elements here. But there are a number of technologies coming out. People are building sort of memory carrier chiplets, for instance, so you can have a kind of a mesh that could sit memory on top. People are putting memory, if you look at what AMD is, for instance, with their V-cache, they're setting their memory, they're stacking it in 3D. There's a number of ways to look at memory here that we're looking at all of them, yes.
Okay, thank you. Very useful clarification. There is a question from the room.
Hello, thank you for your presentation. You mentioned that in order to move to this system on chiplet, we'd also need software to adapt. I'd expect this to be transparent to software. Could you give an example on how you expect software to, what changes are needed for software to adapt in this case?
So the absolute goal is to make it transparent, and that's an area that it's going to need a lot of work, right? So in the end, if I compare, for instance, just a simple example, if I compare AMD to NVIDIA, NVIDIA has developed CUDA. CUDA actually hides a lot of the complexity from end users. If certain end users will get access to some elements, but if you take CUDA out of the box, it actually hides a lot of the complexity, and you don't know what's going on under the hood. You're just accessing features. That's the right way to address customers in the beginning. And then as certain customers need more access, or let's say can get more advantage from touching elements at a lower code level, or even sometimes at the register level, you can make that available. AMD has had less success because of their software stack. It's a hard thing to get right. How do you balance that? And it's a lot of work underneath to make it look simple. So when software is simple, it means somebody's done a lot of work to make it simple. Right? So ideally, you're making calls to the processor and you have some knobs that you can turn to access the acceleration. And the goal in the beginning is to keep that as simple as possible, and then sort of like an onion, offer more and more layers of complexity that customers who can take advantage of this can access. That's the thought process we have in terms of the software layers. I don't know if I answered your question exactly. That was very high level. If you want more detail, you need to talk to some of our software guys, because I'm going to run into limitations on what I can actually address.
Thank you.
But the key here is a good out-of-the-box experience for the customer. If the customer has to take 2 weeks to even get things working or understand the structure of things, it's going to sit on the shelf for months, I guarantee you, unused.
One further question from the room.
Hi, this is Vasilis from Ford. Thanks for this great presentation. So my question is mostly around the economics of chiplets. So do you see what do you expect in terms of volumes for a chiplet to be financially, let's say, viable for future architectures, or maybe even how could the price of a chiplet be competitive in the future?
So if you look at it from a yield perspective, there's a number of analyses that have been done. If you look at it from a yield perspective, especially when you're in low nodes, right? So assuming that, let's say, the CPU has to be at least in 5 nanometer or lower, then And if you're building big chips as CPUs or GPUs, accelerators are today, those are quite expensive to build and your yields are poor. As you break that up into smaller blocks, you can get more chiplets onto a wafer and you get a higher yield for the chiplets themselves. Then the question becomes, what's your yield in packaging? And if you go through the math on this, and there's a number of calculators online, this actually works out that building chiplets in 200 to 300 millimeter squared format is going to give you a much higher yield than if you're building, 600 or 650 for a single chiplet. So the economics of chiplets in this sense, in this structure, makes sense. Now you have to yield the package itself, and that technology is getting better and better. And you have to have, now you have to have people who can guarantee the yield of their chiplet, because as I'm putting chiplets in a package, if one of them is bad, I can't just pop that out and pop another chiplet. I throw everything away, right? So it's very expensive to not test well these chiplets themselves before they go in the package. So that's one of the ecosystems that we see that has to continue to evolve. How do you test at the wafer level to find the majority of faults? How do you move testing forward in the process in the manufacturing stage so that you have known good die with very good performance, or very good yield, I should say. So that's something that people are working on today, and the manufacturing houses are working on. So from a pure packaging perspective, we see a gain in terms of yield. Beyond this, then you talk about volume. So now somebody's got to go out and actually have to build their chiplet. Volumes will depend on what technology node you're in. And again, if you look at this slide here, you see, you might have an accelerator in 5 nanometer, you might have sensors in 28 nanometer, analog portions in 22. So you can build your technology in, let's say, the largest node that still works for you. And the nice thing about the UCIe today is that you have this up to 28 nanometer. You have the UCI interfaces that can potentially interface with chips down to 3 nanometer or even 2 nanometer as we go forward. So having this range of connectivity possible allows the chiplet developer to develop in whatever node makes sense. So you have a cost savings here across the entire package, and certainly for the individual developers of the technology. So that's two ways we see a real value in terms of the system on chip versus a monolithic design. The other way that you're going to gain is on reuse. So once I've done a chiplet, if I scale this in an intelligent way, let's say, for instance, I want to make Rhea 1, which is 80 cores. If I made that in chiplets and each was 20 cores, and this is something AMD does very well, by the way. So AMD builds chiplets that are 8, 16 processors, and they reuse those processors in both their PCs and in their servers. So those chiplets themselves, not the processors, but the chiplets, will go into different kinds of applications. So as long as I can reuse and have scale, then I get another gain, which is I can scale this into different types of products, and it becomes a building block technology. So those are the ways we see real gains in the chiplet architectures. But again, it requires a very good work up front in terms of how do you segment these architectures and the different elements into the different chiplets. And then what are your performances across those interfaces? Because those interfaces between chiplets now potentially become bottlenecks. That was a really long answer, sorry.
Any other question from the room? Or any of the other remote attendees? Okay. If not, thank you very much, Craig. Very good presentation, lots of things to think about. I hope there is a chance for us to pick up the slides for public dissemination. Perhaps. Sure. Again, we appreciate that you took the time to contribute today. Thank you very much.
Thanks all.